In this video, we will be discussing types of sedimentary rocks. Sorry if the quality on the camera is really bad. It's a very old computer because my computer's webcam doesn't work. Alright, so what are sedimentary rocks? Sedimentary rocks are formed through the accumulation of sediments. They come in several types, including detrital, or sometimes called clastic sedimentary rocks, chemical sedimentary rocks, and biochemical/organic sedimentary rocks. Figure 2a is a conglomerate, which is an example of a detrital sedimentary rock. Picture 2b is an example of a chemical sedimentary rock, and picture 2c is an example of a biochemical/organic sedimentary rock. You can see in 2c the rock contains shell fossils, which indicates the fact that it's a biochemical sedimentary rock. Detrital sedimentary rocks are made from the process of mechanical weathering. This means that they have been produced by being transported, consolidated, or deposited. Chemical and biochemical sedimentary rocks are the end products of chemical weathering. Under certain conditions, chemicals become concentrated enough to precipitate from solution. If this process is entirely inorganic, it forms a chemical sedimentary rock. If the process is helped by organisms, for example chalk, which is made up of the skeletal remains of microorganisms, then it is a biochemical/organic rock. The appearance of sedimentary rocks. Appearance of sedimentary rocks varies through their texture and other features. When looking at detrital rocks, we look at their grain size, composition, and the shape of their class, which are the loose fragments featured in the rock. When looking at chemical sedimentary rocks, we look at their interlocking crystals. When we look at biochemical sedimentary rocks, we look at the fossils they contain. The picture included in the slide is a biochemical/organic sedimentary rock, and you can see the shell fragments featured. These features reveal information about where the rocks originated. For example, fossils in biochemical sedimentary rocks can reveal where the rock originated and details about the life form. Detrital sedimentary rocks. Detrital sedimentary rocks are a product of mechanical weathering, transport, and deposition of solid material. These are also called clastic sedimentary rocks based on the class we can see in the rock, also known as loose grains. In figure 4a, you can see the various class and loose grains featured in the rock. They vary in appearance, texture, and size. The loose grains featured in the rock were eroded from their original location and transported. The mechanism of transport for these rocks is either mass wasting or erosion. Between the class is finger-grained material called the matrix. All detrital sedimentary rocks have a clastic texture, yet they vary in these features, including grain size, class composition, and grain shape. These features are other indicators of the environment in which they were deposited. Detritus class are generally composed of fragments, rocks, or individual minerals such as quartz, feldspar, mica, or clay minerals. These minerals that are included in the rock can help geologists identify where source rocks were exposed. For example, some of the detritus that has accumulated at the mouth of the Mississippi in southern United States came from source areas in the continental interior of North America as far away as Wyoming, Ohio, and Minnesota, various parts of the United States. Another example is continental ice sheets transporting giant boulders over great distances, only to drop them once the ice finally melts. For example, boulders deposited in northeastern Kansas consist of a distinctive collection of rocks such as basalt, iron deposits, and quartzite that were derived from bedrock hundreds of kilometers to the north. Ice sheets incorporated these boulders as they advanced southward from Canada to Kansas. The agent of transportation also affects the rocks. If the agent of erosion is running water, various minerals such as quartz, feldspar, mica, and clay minerals that make up the detritus behave quite differently. Quartz and muscovite, for example, are both chemically very stable. However, quartz is physically stable, unlike muscovite. Quartz can survive many cycles of transport and deposition, while muscovite is physically fragile and unlikely to transport well. Because of this, scientists can conclude that presence of muscovite in sedimentary rocks indicates nearby sources of muscovite. Feldspar is additionally chemically unstable. It tends to break down by reacting with water, forming clay minerals. Because of this, it breaks down before it can form a sedimentary rock. Feldspar accounts for about 60% of the mineral content in source areas, but only about 10 to 15% of mineral content in average detrital sediment. Additionally, minerals such as olivine, pyroxene, and amphibole are also unstable and readily break down during weathering and transportation. When these are found in detrital sedimentary rocks, it can be assumed they did not travel far. Quartz and clay minerals are chemically stable, so they are dominant minerals in detrital sediments that traveled far. Grain size. Particles of the same size, shape, or density are naturally selected and separated from dissimilar particles through a process called sorting. The degree of sorting can provide clues about environmental conditions at the time of the deposition. Desert sand, for example, is typically made up of wind-blown grains, and wind is a very effective sort of detritus, so the grains it transports are all similar in size. On the other hand, glacial ice is very unselective and transports detritus that varies widely in size, so it is an example of poor sorting. Steam is one feature that can vary depending on its energy levels. In a high-energy environment, steam can transport large boulders as well as fine particles, but in a low-energy environment, water is a more effective selector of grains, and the volume of water traveling downstream is much lower. This makes a low-energy steam environment a better sorted deposit. Grain shape is also affected by transportation. In a process called rounding, sharp edges are modified during transport. Sharp corners are chipped off by impacts with other grains or the bed of the stream. Grain size becomes smaller and fragments become more rounded as fragments move farther away from the source rock. Other more subtle changes to grain shape provide evidence about the journey particles have taken. For example, during wind transport, grains become pitted and polished by mid-air collision, or transport by ice can carve grooves, which we know as striations, on the grain surfaces. Chemical sedimentary rocks. Chemical sedimentary rocks are considered non-clastic. They are made up from interlocking crystals instead of clasts, which are the loose grains we discussed. These rocks that form through chemical and biochemical sedimentary processes are also less common than detrital sedimentary rocks. Chemical sedimentary rocks form from the precipitation of crystals from solution. They have a non-clastic texture with interlocking crystals, and in hot, dry climates, water evaporates, leaving dissolved ions behind. Concentration of these ions in the remaining water consequently increases, eventually reaching a maximum threshold known as saturation. Crystals form from those dissolved ions and grow until the pore spaces between the grains are eliminated, producing a texture of interlocking crystals. Evaporites are a family of chemical sedimentary rocks that form by the precipitation of salts left behind by the evaporation of seawater. Evaporite deposits of salt and gypsum are examples of chemical sedimentary rocks, and they are entirely inorganic. Evaporite deposits from the Mediterranean Sea dried up between 5 and 6 million years ago when the Strait of Gibraltar, which connects the Mediterranean to the Atlantic. This closure left the Mediterranean as an isolated sea in a warm climate. Sea level fell, causing dissolved ions to concentrate until they precipitate. As a result, evaporite deposits have been found in many localities at the bottom of the Mediterranean Sea. This is an example of formation of chemical sedimentary rocks. Biochemical sedimentary rocks. These are also called organic, as they are made by processes of organisms. Some examples of biochemical sedimentary rocks are peat, lignite, and coal. These are all known to be plant fragments. Other examples include remains of shells, reefs, and corals. Sometimes we classify these as limestones. These are formed by organic processes and commonly contain fossils of the organisms responsible for the formation. Marine organisms can absorb ions such as calcium, magnesium, silicon, iron, and phosphorus from seawater to form their soft tissues or their hard shells. When organisms die, they settle to the seabed and become compacted into biochemical rock. Another biochemical sedimentary rock, such as coal, which forms from the compaction of plant remains, are valuable natural resources and provide important clues for unraveling ancient environments and climate patterns. Can we consider rocks for multiple categories? Well, limestone is an example of a rock that can be considered both chemical and biochemical in origin. What it's called depends on the environment in which it was deposited. Limestone is a common sedimentary rock, and it is composed primarily of calcite. It can form in a variety of ways, one example being formed in the warm, shallow seas of the Bahamas, where the concentrations of calcium and carbonate ions in the ocean are so high that calcite precipitates as chemical sediments. Shells roll back and forth along seabed as a result of strong tidal currents. Calcite crystals precipitate from the seawater and coast the rolling shell fragments. Limestone forming in this manner is oolitic limestone, and it's considered chemical. In another environment, calcium and carbonate ions are extracted from seawater by marine organisms to form a sediment that is biochemical. Some examples of these organisms are coral and algae, who secrete organic calcite to form their external skeleton. The algae live with them and secrete calcite to help cement and solidify the reef structure. The Great Barrier Reef, pictured in the background of the slide, is the largest structure ever built by living organisms. The structure is made of coral limestone, which is biochemical in origin and consists of abundant fossils cemented by crystalline calcite. The texture of these limestones are made up of interlocking crystals of calcite and are considered non-clastic. So, the important things we learned from this slide is the difference between detrital chemical and biochemical sedimentary rocks. Detrital sedimentary rocks are the processes of mechanical weathering. Chemical sedimentary rocks do not contain the class and are made up of interlocking crystals, while biochemical sedimentary rocks are made with the help of organisms.